Stefan Kolling is a professor at Technical University of Mittelhessen in Germany. He is specialized in fields in terms of developing material models, failure criteria. So he and his staff developed a beautiful material model for catch the fracture behavior of glass, laminated glass for windshields. So this is a really beautiful fracture model for windshields, which is available now in OpenRadioss and in automotive. So it's very precise predicting of fracture of glass in terms of occupants or pedestrian impacts, things like that. But not only this, also for civil engineering, buildings, as well as for electronic devices like cell phones, tempered glass, thermal treated or chemical treated glass, where you have different stiffness gradient through thickness in very thin glasses. So this is all done now and implemented in OpenRadioss, which predicts very well. You saw the videos on LinkedIn, the drop tests of the cell phones with this very hard glass on it. And now, so this was a funny story because here we were 2 years ago in a conference at the INEC in the US. And so we were sitting together in New Orleans in the French Quarter, so having some nice colorful drinks. And then the idea comes, so he told me, Marian, what we are observing in glasses are sometimes that they are not well produced or getting older. So there's moisture effect of air or other things which go inside into the glasses and create delamination and damaging inside, or in other applications also creating the dendrites which are damaging the very thin layers of our glasses. So, and we would be interested what happens if then these kind of pre-damaged glass structures or whatever structures, polymers, will be loaded due to whatever load case. So at that time, then we thought, okay, let's have a look on reality. Let's catch some pictures and then see some nice patterns like these. So it looks like fractals. If you zoom closer, so the structure repeats itself. So there was already such kind of idea. So if you see everywhere, you see, if you zoom closer, you will see these beautiful fractals, or here due to ice, or these kind of things. So, and then we thought, oh, there was already someone who invented it, which was Benoit Mandelbrot, a French mathematician, and he did these kind of pattern which he invented at that time. So, and these pictures become very popular 30 years ago, where the computer become more powerful. So today it's very simple, very easy. But at that time it was something completely new, mind-blowing. Have this kind of fractal patterns which repeat if you change the scale all the time, everywhere. So, and we thought, okay, can we do something like that for predicting this kind of damage which occurs sometimes in materials which we see, which we observe, so we cannot neglect it. So can we deal somehow with these things? So if you zoom in here in this area, you will see the repetition of this pattern always, and especially in laminated glass, which consists out of 2 plates of mineral glass and a polymeric interlayer in between, usually PVB foil. So this is how it is produced. And then we saw in reality, this is, for example, this kind of damage which occurs when moisture or air or whatever is going into this interlayer structure and is creating this kind of fractal damage on the boundary of these glasses. But here in civil buildings, so we see it sometimes in windows, it's in the middle. This kind of pattern which exists, you can see it sometimes. in older buildings, for example. Or that one, which I observed also a few years ago, so I immediately took a photo of it. It was on a wall. There's also here, if you zoom in, you see repetitions of these pattern, however. So, and then, so the pre-location which we talk about is originally developed for vulcanization, by Paul Flory. So lattice representation with occupied points. So L times L lattice describes a 0-1 phase transition. So this is the impression what we have here. So if this transition of whatever, can be moisture, can be anything, is now getting into the structure and it's formulating clusters due to whatever probability. So here we see the accumulation and growth of these kind of structures, where this formulation of clusters is increasing when a certain level of probability is reached. And you see then, if one piece enters here, it has a probability to stop somewhere or not. So, and this is what we call the drunken walker approach, to create these kind of patterns based on this probability. So, and we are sitting and thinking, okay, this is a random walk approach, which we have then implemented to create this kind of pattern based on this drunken walker approach. So, formulation of an infinite cluster. So there's a critical value, PC, which depends on the grid type for which an infinite cluster forms for periodical boundary conditions. So, and we see the percolation example. So on a grid size, which we then see a number of clusters versus the probability and time to form an infinite cluster increases with the probability P. So the fractal geometries in the independence of the probability usually is a function for a fractional number. So, and we added these values, or we played with it a little bit first on some very simplified examples before implementing it. And later on, so this is also an acid corrosion through a container wall. It's a phase transition through the grid, and you can see it depending on the probability, the increase or the phase transition, which is getting now into this structure. So diffusion, limited agglomeration. So this is what we called it, where we can define a starting point for this, and we define the number of particles which start somewhere here at the starting point, and then we are doing a random walk, and at a certain point, if this random walker hits the boundary, he falls off and is dead. So then we start a new one, a new walker. So at a different position and so on and so on. We have thousands of walkers which we start. And once they hit here or getting closer to this nucleus, the neighboring position, they reach a neighboring position, they stay, which means they're getting here stopped and creating a cluster. And then starting the next walker. Walk ends if the particle reaches the neighbor position cluster, damage growth, or when the particle leaves the lattice. So, and here now we can play with the probability, and if the probability is changing the shape or the density of these kind of patterns, is also influenced by these values. The smaller P0, the denser the surface. So we can start also from the edge then we can see these kind of patterns. And this is one picture from reality, what reality shows. And viscous fingering are somewhere in the center. And this is also what you quite often observe in structures, glasses, in polymer foils. Then we can also compute the radius of the aberration, defines the damage area. So this is also things for post-processing. And then we implemented it. So we coded it. First, I did it as a user subroutine to pre-damage the structure. This is not the failure criteria. So you apply a pre-damage, and then you apply your material model and your fracture criteria, whatever it is. It can be anything. But then you have a structure which is somewhere on your windshield or glass. So this is a large glass piece. So these are the small pieces are the FE, finite elements. So it's a very fine mesh, but whatever, it can be the size of this window here or the size of the smartphone or whatever, with a lot of elements. You define your starting point, you define your whatever first ending point, agglomeration point, or you don't do it, so you let it fully to be random. Starting point can be totally random, ending point can be totally random, or you define some because you have observed it somewhere on the structure. So it's fully flexible. Then you define the probability value, and then you let it run. It's in the starter, it takes just 1 second, and you will obtain this kind of pattern based on pre-damaged structure, where you then apply your material model and your fracture criteria, and you continue with your real load case. It can be drop test, it can be a ballistic impact, it can be anything else. But you already have a structure which represents the reality. Here, for example, if we compare now image 2 and 7, which is this guy and this guy. So 2 and 7 in comparison, so the starting point is here, and the nucleus, the yellow point, is usually is in the middle left here. So it starts here, and in the middle is the ending point. And we use the random walk approach. So most of the nuclei which started are getting to the edge, then they are dying. Nothing happens. But some of them are reaching here closer, and then with a certain probability, they stay. And then the next random walker will start its walk and proceeding. So here, these two pictures represent two different runs with the same settings. So, and this is for typical for radios. This is a feature which means parallel arithmetic, which means if you change the number of CPUs or you do several repetitions, you will obtain exactly the same results. So we can guarantee this. If not, then there's a bug. So otherwise, you will get exactly the same results. Again, this is a feature. You can switch it off. So then you will not get the same results. But by default, it is on. So how often if you repeat the runs, you change the number of CPUs, you will obtain exactly the same results, because here behind these, we have a huge number of random, let's say, random number generations. So, and a random number generator is not really a pure random value generator. It's a kind of mathematical equation. So there is no real random number in the computer science. Anyway, but for that, this is not what you observe. In reality, you observe different patterns. So we want to have this change. Therefore, we have also added this C value. So you can tune or change the starting parameter for the random number generator. Then you will obtain different results. And here, if you repeat, do not no change in the model, but just run it twice, and you see, for example, here or here. So there are slightly differences in the results. tiny differences, but there are differences. If you now do several repetitions of this run and change the seed values for the random number generator, you can do robustness investigations of your whatever, of your part of your system. So to check how robust the design will behave, because the pattern will be always slightly different. But again, we still define the starting point and the ending point, which is in the middle. Now, if we have also the possibility to change the number of the initial walkers, which start their walk and their journey. For example, oxygen or hydrogen behave different in these things, so the pattern will look different. So depending on the materials here which we use. And then we can change for sure the starting point, so then the pattern will change. Or we do not have any starting point, so the starting point is random, then we'll get this kind of circular pattern in the center where we have still the ending point of for these random walkers. And this is also what we are observing in reality here as a photo from a glass. So this spherical structure is created without preferred orientation. The same effect can be observed in real glasses. So like we took a photo here from this part. There's also a larger project now in the civil engineering ongoing using this approach to test it. So here, image 8, same as image 2, but the starting point is in the middle, so different direction. This is also starting point is here, and this edge or corner. And you have the control now over the patterns, or you let it to be fully random. You can set also several values for several starting ending points. So now we study the damage evolution in the event of hail impact on windshield, define the weight of the and size of the hail, determine in initialization and growth of fractal damage via DLA, nonlinear explicit FE simulation using OpenRadioss. So, and this is what we observed. These are hails, which we already observed. This is a photo from reality, but you can also have these guys here. These are a little bit more dangerous, but still observed in reality. And then we used it on a windshield. So one is pre-damaged like this. So this is still before the impact. And so this is a new, let's say, fully healthy windshield, and this is pre-damaged with these kind of patterns, which we created before the simulation, the load case, the impact starts. So, and then we see in the non-pre-damaged windshield, nothing happens after the impact. With the pre-damaged windshield, we see fracture using the glass failure model. So this is what I mentioned to you today morning. We have these models for failure for glass. So to do your glass simulations, you can use exactly this. This is free, available. You can download it. I can show you where. So it contains already the glass fracture. And then we validated, which is important for pedestrian protections, for example, the acceleration, then which you will measure, or the head will measure the pedestrian protection head. And for this, let's say, virgin glass, so we see a high acceleration or deceleration, whereas for the pre-damaged glass, much lower, which is better for the occupant, but for sure not so good for the windshield itself. The damaged windshield is significantly softer than, and therefore better in the event of a head impact. This is good, but who wants to drive with a damaged windshield? Anyway, we tested it as well. So Stefan Kolling's lab has the possibility of doing these tests. So for development of this glass fracture model, it took us 3 PhD theses, around about 10 years of research. So now it's available. It's now being also transferred into LS-DYNA, but it will maybe take time. In Radioss, it's already available since 2 or 3 years. So this is the impact we are talking about. And yeah, that's the end of my presentation, and thank you for your attention.